Hey everyone, good morning, afternoon, evening, nighttime, whatever it is when you're watching this. For today's video, we've got one more optimization problem. This one's going to be a doozy. It's kind of one of the hardest ones it can be. So make sure, don't write super huge on your page, and just strap in, fasten your seatbelt. It's the only problem we got to work today. So let's take a second, let's get down to business and read the problem. What are the dimensions of the lightest open top, right circular cylindrical, it should say cylindrical can, that can hold a volume of 500 cubic centimeters? Okay, now the first thing I'm going to concede to you is maybe I've not made it super clear what it is you're trying to optimize, or when you see lightest, you think we're going to optimize weight. And that's not my intention for you to think that way, so I'm just going to give it away here. My goal is for us to minimize surface area. So we're going to minimize surface area. So that's just kind of my mistake for using the word lightest. I mean, something with minimal surface area would probably be the lightest if it's made out of the same material, but I don't want to make that claim for certain. And then I see volume of 500 cubic centimeters. That sounds like a constraint. So constraint V equals 500 cm cubed. So let's talk about surface area, because if that's the thing we're trying to minimize, then we should probably come up with a function that represents surface area. Well, it's the open top, okay? So we've got an open top, and then it's a cylindrical can, but the bottom's going to be enclosed. So we don't need the top, but we do need the bottom. And then we also need something that represents the sides. So let's think. Well, the bottom of a can would just be a circle, right? So the bottom, its surface area is just going to be pi times its radius squared. So let's draw a radius on there, r. And then I need something which represents the outside face here. So let's think. Well, really, if we could take a pair of scissors and cut this somewhere. Whoops. Oh, that was never going to work. Oh no. I wanted to cut it right here. If we were to take this somewhere, ignoring the top and bottom, if we cut this somewhere and then we flatten it out, wouldn't you just end up with a rectangle? If you don't believe me, what I want you to do is just take a piece of loose leaf paper. You can't see me, but grab yourself a piece of loose leaf paper, and if you fold it up into a tube, you have a cylinder with an open top, open bottom, right? And then if you unwrap it, you have a rectangle. So hopefully I've convinced you that we can take the body of that tube and make a rectangle. So normally you'd say it's got a base and a height. Well, we can still use the height. The height's going to be pretty important. But if we use base and height, we got three variables: radius, base, and height. So we should probably try and get rid of one of these right off the bat. And the base, wouldn't that just be the circumference of your trip around the tube here? Okay, well, we can't use C. C doesn't really solve our problem because we'd still have another variable here. But I do know that circumference, thanks to my knowledge in geometry, is double the radius times pi. Pretty convenient, right? So our total surface area is going to be pi r squared for the bottom plus 2 pi r, or 2r pi, whatever, times height. And in fact, it's going to, I actually hate that I wrote 2r pi, so it's going to be 2 pi r. I'm just going to switch the order of these because I want my variables together. So obviously, if you just memorized the surface area of everything, that would have been fine too, but hey, look, we figured it out ourselves, no problem. So that's what we want to minimize. Now we got to figure out a way to get the constraint there, because right now I have two variables. I have r and I have h. That's no good. I need to get down to something of one variable, that way I can derive it. So let's see. I know my volume is 500 centimeters cubed. What would the formula be for the volume of any cylinder? Well, the good news is we can also figure this one out on the fly, even if we didn't memorize it in geometry. So let's go back to how you find like the volume of a cube. So it would be base times height, or base times length times height, right? So there's our length, and then there would be height. And oh God, we're about to see exactly how terrible I am at drawing 3D images. Okay. But my point is you'd have a base, a length, and a height. So another way you could say this is you could say it was area times height. Well, we already talked about the area of the base. It's a circle, pi r squared, and then times height. And we know, thanks to our constraint, that that has to be 500 cubic centimeters. So this should help us get rid of one of the variables. I would highly recommend solving for the thing that doesn't require you to, well, how do I want to help you out here? I want to solve for h because it's by itself over here. I don't want to have to solve for r because I'm going to use it in two different places, and one of them's squared and just feels messy. So let's get rid of the h. I guess you could solve for r and that'd be fine, but I don't like it. So I'm not going to do it. Okay, our constraint has constrained. Now let's adjust our original thing. Our surface area function is now a function of just r. I know it's weird to write SA. If you don't want to write SA, you just want to write S or something, that's fine. Pi r squared plus 2 pi r, 500 over pi r squared. And before we even derive this, like I told you before, don't simplify unless you need to, but we're going to derive this. I don't want to product rule it, so we might as well simplify it at least a little bit, right? SA, surface area of r, is pi r squared plus, I see a pi here, I see a pi there. I can do 2 times 500, that's 1,000. And then I have an r here, I have squared here, so I just have 1 behind. So here's an easier way of representing our surface area. Ooh, and I'm going to derive this. So who wants to quotient rule something goofy like this? How about now let's power rule it. Bam. Man, we're so good at this. You guys are so good at this. Since we're trying to minimize, let's take that derivative. Let's set it equal to 0 and check where it's undefined, because I think we're going to have one of those points this time too. Maybe. And then we'll finish solving the problem. So let's derive this with respect to r, 2 pi r minus, because the minus 1 is going to come down here, minus 1,000 r to the negative second power. So then to minimize, we need to find our critical points. Let's set that equal to 0 and talk about where it's, well, let's just do undefined first real quick. Let's say it's undefined at r equals 0. The reason why is because you have, really this is 1,000 over r squared, right? So if r equals 0, divide by 0, universe explodes. Good job, you did it again. Okay, so there's one of our critical values. And the other one then is going to be where 2 pi r minus 1,000 over r squared equals 0. So let's solve. Let's add it over. Then let's multiply off the r squareds, the r squared singular. So that'll give us a cubed on one side. And then finally, let's divide by 2 pi and cube root. I did not take my own advice on writing small. I am sorry. 1,000 divided by 2 is 500. Still going to be over pi. So our radius then would be the cube root of 500 over pi, which let's just leave it like that for now. Okay, so it's undefined when r equals 0. So you might say, okay, well, we got to check this one too. But here's the thing. If r equals 0, h equals 0, our surface area is 0, it kind of trivializes the problem. Yeah, you're right. No surface area would produce no volume. Oh, wait, that wasn't the task. We need to be able to produce 500 centimeters cubed of volume. So 0 straight up will not work because it goes against the constraint. So we're just going to eliminate because it trivializes the problem. It goes against the constraint. Does not fit constraint. Okay, then let's check and see if this is going to be a max or a min, because hey, maybe there's no way to minimize this. I don't really want to derive this again to do the second derivative test, so why don't we do the first derivative test? It's been a while since we did the first derivative test. Let's see. We've got our critical value, which we should probably punch that in a calculator to estimate it then. Fine. I think it's about 5.4. So let's do our first derivative test. Let's start at 0. Let's make our lower bound 0. And then let's just go up forever. So there's 5.4. So this would be our surface area prime, and then our radius values. So pick your favorite number between 0 and 5.4. My suggestion is 1. If we take 1 and we plug it into the first derivative here, you will get, well, you'll get 2 pi minus 1,000, or so probably negative, right? So the first derivative there is negative, so the function is decreasing. And then whatever you want, 6, 7, doesn't matter. Plug it in. I'll save you the time. I'll just tell you the number comes out positive, which means the surface area is increasing. So 5.4 is definitely a minimum, or rather R equals cube root 500 over pi is a min. Oh my goodness, we have to justify this, don't we? Because SA prime changes from negative to positive. Okay, we're done, right? No, we gotta minimize, we gotta actually come up with all the dimensions. It says, what are the dimensions? So we got the radius. What's the other thing we need? Just the height. So I think our constraint can help us out there. Our height was 500 over pi r squared. Let's plug in our answer. So that would mean our height would be 500 over pi cube root 500 over pi squared. Oh my. But it actually cleans up pretty nicely. If you punch this in your calculator right away and you don't try and clean it up, you will curiously find, I assume you're going to find it curious, that it is also 5.419. And if you do want to clean it up just for a fun algebra step, because I know some of you nerdlings are like that, your intermediate step would be cube root of 500 over pi again, which should, I mean, you're probably like Mr. Doolin, that's super obvious because it generates the same number. But I just want to show you that's where you're trying to end up. So to finish, both our radius and our height are 5.419. Make sure you answer in context, centimeters. How do I know it's centimeters? Because we were given volume in centimeters cubed, so I measure everything in centimeters. Okay, I know it was a little bit more, but at its heart, same idea, right? Let's look at our steps from yesterday. We identified what we needed to maximize or minimize. We figured out how to express that in one variable using the constraint. We derived, we investigated the critical points. We threw out one of them. We verified the other one was the minimum we wanted. We made sure that we found everything we needed to, so the dimensions. So good work, everyone. Super proud of you. Looking forward to seeing you tomorrow or whenever I see you. Thanks.